You are listening to The Vocal Technologist. Spoken tech for your ears.
Imagine a single piece of user interface that is looked at 7.67 billion times a single day.
I mean, that number is just, it is hard to even wrap your head around.
Right. It is actually more than the entire human population looking at one specific box on the internet.
Yeah, which is terrifying if you think about it.
It really is.
Yeah.
And it makes you wonder, what happens when that box is completely broken.
Well, you get a massive global friction point straight away.
Spot on. So we are going to look under the hood at the friction points between massive scale web infrastructure, the artificial intelligence tools trying to manage it, and the solo developers who are just fiercely pushing back.
It is a really fascinating tension to pull apart.
It is. Because looking through the absolute mountain of research you sent us to unpack, we're going to explore how the internet handles scale, performance, and, well, just the sheer volume of code being written right now.
Yeah, because on one hand, we have these massive systems trying to serve billions of requests seamlessly without collapsing, And then on the other hand, you have individual engineers demanding absolute control over their own digital environments. And both sides are running into the fundamental limits of how we build software.
And to really start, we need to talk about that 7.67 billion number. Because that is the daily impression count for Cloudflare Turnstile.
Right, the capture replacement.
Yeah, exactly. For anyone unfamiliar, that is the little widget that proves you are an actual human and not some malicious script trying to scrape a website.
Yeah, and the engineering team over there conducted a design audit of this widget. And honestly, the results were a bit of a horror show.
A horror show? Like, how bad are we talking?
Well, they found massive inconsistencies across the board. We are talking wildly different visual layouts depending on exactly where the widget loaded.
Oh, wow.
Plus technical jargon that the average internet user could not possibly understand. And most problematic of all, these just panic-inducing red error screens.
Oh, I absolutely hate those. I mean, if you have ever clicked a button to buy concert tickets and suddenly the screen flashes bright red with some cryptic string of numbers, you know the exact feeling.
You instantly think you did something wrong.
You do. You think you have just deleted the internet or, your credit card has been charged 50 times. It is just a terrible user experience.
Right, and that cognitive load is a massive barrier. It makes users feel at fault when, in reality, the system is the one struggling.
So how did they actually fix it?
The solution required a complete architectural unification. They had to unify the Turnstile widget and their larger challenge pages, so they stripped away the verbose error messages completely.
And replace them with what?
With very short, highly scannable labels. They also had to achieve WCAG AAA accessibility, and they had to do it across over 40 different languages.
Okay, let us just pause on that for a second. Because achieving AAA compliance, it gets thrown around a lot in tech, but it is notoriously difficult to actually pull off.
Oh, it is incredibly strict.
Right. From the notes you provided, it means the color contrast, the screen reader compatibility, and the keyboard navigation, all of it must be flawlessly executed.
Spot on.
It is essentially ensuring that a visually impaired person who relies on a screen reader gets the exact same frictionless experience as a sighted person.
That is correct. It is the absolute highest tier of web accessibility. It means no element can rely solely on color to convey meaning.
Right. So you cannot just say click the green button.
Exactly. And text must have a massive contrast ratio against its background. Plus, every single interactive state has to be perfectly described to an assistive device.
It is kind of like the old design was a nightclub bouncer who just screams NO at you in a language you do not speak.
That is a great way to put it.
And the new design is like a bouncer who speaks 40 languages and just politely explains that, hey, mate, your ID is upside down.
Exactly. But the truly interesting aspect here is not just the design itself, it is the deployment.
Right, because how does an engineering team even begin to test a visual change that will instantly hit billions of eyeballs?
Yeah, you cannot exactly just push that to the live server and hope you did not break the internet.
Absolutely not. So how do they do it?
Well, when you operate at a planet-wide level, minor visual inconsistencies compound into global infrastructure failures.
What do you mean by that?
So imagine a button is slightly misaligned or a translation is just a bit confusing. And let us say it causes a 0.1% drop in completion rates.
Which sounds tiny.
It does. But at a scale of billions, you are suddenly locking millions of legitimate users out of their bank accounts or e-commerce checkouts.
Oh, wow.
Yeah, it completely transforms user experience design from a purely visual discipline into essentially a massive scale mathematics problem.
Right, because every single pixel has a massive server cost if it slows people down.
Exactly.
Which, speaking of slowing things down, React solved a very similar blocking issue by completely changing how it handles traffic jams.
Yes, they absolutely did.
Because if we look at the research you shared on front-end rendering, our favorite frameworks are desperately trying to keep up with the sheer amount of things we were asking them to paint on the screen.
It is a massive bottleneck.
So let us get into React Fiber. Because before Fiber, we had React 15, and from my understanding, it had a rather fatal flaw when it came to heavy lifting.
It really did. And to understand it, it basically comes down to how web browsers actually work.
Okay, lay it on me.
Browsers use a single main thread to do almost everything. It runs your JavaScript, it calculates where an element should physically go, and it paints the pixels on the screen.
All on one thread.
All on one single thread. Now, React 15 used a recursive model to walk through the component tree. So when the application state changed, React would start at the top of the tree and just recursively update every single component downwards.
And because JavaScript is single-threaded, I'm guessing this recursive process completely monopolized that main thread.
You guessed it. Once it starts, it literally cannot be interrupted.
It is like a stubborn chef who just refuses to chop the next onion or answer the kitchen phone until the current massive pot of soup is perfectly plated.
Yeah.
The entire kitchen just grinds to a complete halt.
That is a brilliant analogy. Any heavy rendering task would completely block the browser from registering new user input until the entire update was finished.
You would try to scroll the page or click a button, and the browser would just freeze.
Exactly, because the main thread was trapped inside that recursive React loop. So to fix this, the core team had to completely rewrite the architecture.
Wow. What did they replace it with?
They threw out the recursive model entirely and introduced a linked list data structure, which they called Fiber.
Okay, so instead of the browser call stack dictating the work, React takes control of the scheduling itself. But how does a linked list actually solve the freezing problem?
Well, a linked list allows the framework to break the rendering work into individual discrete units. And because each unit of work knows exactly what the next unit is, Fiber can pause the work, it can prioritize different tasks, and most importantly, it processes work in tiny chunks of about 5 milliseconds.
5 milliseconds. That is incredibly fast.
Yeah, and after each chunk, it actively yields control back to the main browser thread.
Ah, that makes complete sense. So by yielding control, the browser has a tiny window to say, wait, the user just clicked the checkout button, let me handle that first.
Precisely.
It makes the entire application feel exponentially more responsive because you are never waiting more than 5 milliseconds for the system to at least acknowledge you.
Spot on. And, we see very similar blocking bottlenecks happening on the back-end infrastructure, too.
Right, Python.
Exactly. The Python programming language suffered from incredibly slow startup times for years, purely because of how it handled eagerly importing code libraries.
Oh, let us unpack the absolute saga of Python lazy imports. Because eager imports mean that when you run a Python script, the interpreter stocks whatever it is doing, goes to your file system, and loads every single library declared at the top of the file before running your actual logic.
Yes. And if you are building a tool that imports a massive machine learning library like Pandas or NumPy, but the user only wants to execute a tiny utility function,
the system still forces you to pay the massive performance penalty of loading that entire heavy C extension into memory.
Exactly. It is incredibly inefficient. It makes command line tools built in Python feel extremely sluggish.
Which is why the community proposed a global lazy import system, right? They wanted to fix this permanently.
They really did. That was the initial proposal, known as PP690.
Okay.
It aimed to make lazy imports the default behavior across the entire language. Under that proposal, a library would only be loaded into memory at the exact moment a function from it was actually called.
Which sounds brilliant. But it was ultimately rejected by the Python Steering Council, wasn't it?
It was, yeah.
Why reject something that makes the language dramatically faster?
Because of the massive scale diplomacy required in open source software.
Ah, the politics of it all.
Exactly. The primary fears were that a global switch would effectively split the Python ecosystem into two totally incompatible worlds.
Because some libraries actually relied on the old way.
Right. Libraries that relied on the side effects of being eagerly imported would suddenly just break. Furthermore, it would require incredibly deep, complex modifications to the underlying CPython interpreter.
It is just fascinating how much careful negotiation goes into these massive projects. It is never just about writing the fastest code, is it?
Not at all.
It is about politics, consensus, and, not destroying millions of existing corporate projects that rely on the old behavior.
But the problem of slow startup times still desperately needed solving. So years of intense debate finally led to a refined proposal, PEP 810.
And this one actually made it through.
It did. It gained unanimous acceptance because instead of changing the global behavior and risking a split ecosystem, it introduced an explicit lazy keyword for individual imports.
I see. So developers could opt in on a case-by-case basis.
Exactly.
We are so obsessed with making code run efficiently and smoothly, which, honestly, is extremely lucky because artificial intelligence is positioned to generate absolute mountains of it.
Oh, without a doubt.
I was reading a piece in the research you provided about a software developer who has completely stopped typing out code.
Yeah, that was a wild read.
Right. They just shifted exclusively to prompting and reviewing output from large language models, and they're completing heaps of complex projects this way, because apparently that is where we are now.
It is a massive shift in how we define software engineering. We are essentially moving from syntax generation to logic verification.
Which sounds exhausting in its own way.
It is, because this proliferation of machine-generated code introduces an entirely new class of problems. We are no longer just dealing with syntax errors that a compiler can easily catch and warn you about.
Right, because the machine does exactly what you ask it to do, even if what you ask it to do is fundamentally flawed.
Exactly.
It writes syntactically perfect code that houses these incredibly subtle logical hallucinations. So how do engineering teams actually manage this absolute avalanche of code?
The tooling ecosystem is having to adapt incredibly rapidly to keep up. Anthropic, for instance, launched Claude Code Review specifically targeted at enterprise users.
Okay, what does that actually do?
It integrates directly into the version control system to act as an automated reviewer for pull requests.
For those who might not live in GitHub every single day, a pull request is just a developer asking the main team to review and merge their new code into the main project. So Claude is just jumping into that review process automatically.
Exactly. Its entire purpose is to scan this high-volume, machine-generated output and catch those subtle logical errors or security vulnerabilities before human reviewers even have to look at them.
It operates as a first line of defense against the avalanche.
Spot on.
Okay, reviewing code automatically is one thing, but then you have platforms like terminal use. From the notes you shared, they provide managed infrastructure for Codex and Claude agents, giving them full native branching, versioning, and rollback capabilities.
That is correct. Terminal use specializes in what we call file system agents.
Right.
These are not just chat boxes on a web page. These agents are given access to read your local files, write new code, execute it in a terminal, run tests, and actually produce final deliverables for complex applications.
I am sorry, but I have to push back on this a bit.
Go for it.
We are giving artificial intelligence file system agents the ability to independently read our files, execute terminal commands, and produce final deliverables.
We are.
That sounds a bit like letting a very enthusiastic toddler organize your corporate filing cabinet, which, yeah, is exactly as terrifying as it sounds.
I completely understand the skepticism there. I really do. It requires an immense amount of trust and very strict boundary setting.
I would hope so.
The containment strategies, the sandboxes for these agents, are just as important as the agents themselves. If an agent hallucinates a command to delete a directory, the sandbox absolutely must prevent it.
That makes sense.
But this autonomous generation brings up an even more complex issue. If these systems are writing all this code by training on existing open source repositories, who actually owns the final product?
The ownership question. It is a massive legal gray area right now, and it is clearly causing a lot of friction.
Huge friction. Let us examine the controversy around the Chardette Python library.
Okay.
This is a widely used open source tool that detects character encodings. And a developer used artificial intelligence assistants to completely re-implement the entire library from scratch.
Just clone the whole thing.
Essentially, yes. And prominent figures in the tech community argue that this is legally permissible under current copyright law and that it actively promotes knowledge sharing.
But hold on, just because something is technically legal does not mean the community accepts it.
Yeah.
Re-implementing a library using a machine that trained on the original library It feels like a massive loophole.
It really does, and it raises a vital question about the difference between legal compliance and social legitimacy.
Because open source relies heavily on copyleft licenses, like the GPL.
Right. Copyleft is essentially a social contract. It says, if you benefit from this open source work and modify it, you must share your new modifications under the exact same open terms.
It prevents massive corporations from stealing community code and just closing it off.
Exactly.
So if a developer uses artificial intelligence to simply launder the logic of a copyleft library and rewrite it entirely from scratch, they just completely bypass the license.
Yes.
That entire social contract just begins to fracture.
Precisely. The machine absorbs the logic but entirely discards the legal protections, which perfectly explains why we are seeing a massive counter-movement of digital independence from solo developers.
People are violently pushing back against this kind of centralization and loss of control.
Oh, absolutely.
There is a great example in your notes of a developer who built an entirely custom website for the sole purpose of archiving photos of pies that they extracted from Instagram.
Archiving pies? I mean, that sounds incredibly niche.
It is absolutely
Okay.
niche, but the motivation behind it is really powerful. They wrote custom scripts to programmatically extract their data from the platform exports just so they could own their content independently.
They wanted their own space.
Exactly. They wanted a piece of the internet that they entirely controlled, totally free from algorithms and corporate policy changes.
It makes a lot of sense.
And my absolute favorite example of this independence is a developer who spent an obscene amount of time building a solo Emacs configuration.
Emacs being the highly extensible text editor that programmers have been customizing for decades.
Right.
It is famous for being completely programmable.
Yes, and usually people install dozens of external packages created by the community to make Emacs do what they want. It is a massive web of dependencies.
Right, you just pull in what you need.
But this developer built a highly complex environment using 35 self-written Lisp modules and absolutely zero external packages.
Zero.
Zero. Everything was built from scratch using only the features built directly into the editor.
Wow, that level of dedication requires a truly deep understanding of Emacs Lisp. It is a total rejection of the dependency culture we have built in modern software.
It really is. I mean, today, a simple website might rely on 10,000 different packages written by total strangers.
Exactly.
It's kind of like building a log cabin in the woods from scratch, using trees you chop down yourself, just to escape the chaotic rent prices of big tech city.
That is a brilliant way to picture it.
You own every single nail and floorboard, you know exactly how it was constructed. But of course, it also means if the roof leaks, you are literally the only person on earth who can fix it.
It is the ultimate trade-off between convenience and technical sovereignty. And interestingly, even the massive tech giants are realizing that absolute unrestrained access to data is becoming a massive liability.
Really, the giants are pulling back.
Yes. We are seeing a structural shift where the absolute best way to handle sensitive data is to architect systems that never actually look at it in the first place.
Let us unpack that because Meta implemented something called advanced browsing protection in their Messenger application. And the engineering behind it is properly wild.
It is a brilliant implementation of privacy-preserving technology. So Messenger uses end-to-end encrypted chats, meaning Meta cannot physically see the content of the messages you are sending.
Because the encryption keys exist only on your device.
Correct. But they still have a major responsibility to protect users from clicking on malicious phishing links sent within those private chats.
So how do you verify a link is dangerous if you are mathematically barred from reading the link?
Well, they use a continually updated watch list of dangerous websites combined with complex cryptographic primitives.
Okay, you might need to break that down for me.
Sure. It operates similarly to a theoretical concept called private information retrieval. When a user receives a link, their local device generates a cryptographic hash of that link. A hash is essentially a unique digital fingerprint.
So the phone turns the web address into a completely random string of gibberish.
Exactly. The system then queries the server using a specialized protocol that allows the server to confirm if that specific fingerprint matches any known dangerous site in its database.
Okay.
The brilliance is that the mathematics guarantee the server can provide the yes or no answer without ever learning what the actual hash was or what the original link was.
That is mind-bending. The server answers the question without ever knowing what the question was.
Exactly.
It's like handing a librarian a locked box and them telling you if the book inside is dangerous without them ever opening the box.
Spot on. It protects the user from devastating phishing attacks while rigorously safeguarding their privacy from the platform itself. It is a zero-trust architecture applied directly to user safety.
And we are seeing this exact philosophy of isolation applied to database management as well.
We really are.
Looking at the Postgres 18 update in your research, they introduce a feature that solves a massive headache for data engineers. It allows you to export production optimizer statistics into non-production databases.
This is a crucial development for safe testing.
Tell me more about that.
So the query optimizer in a database like Postgres is essentially the brain that figures out the fastest possible way to retrieve your data.
Right.
But to make intelligent decisions, it needs statistics about the shape of the data, like how many unique values exist in a column or exactly how the data is distributed across the tables.
And historically, if a complex query was running painfully slowly in the live production environment, an engineer had to test it against the actual live data to figure out why the optimizer was getting confused.
Which is a massive security risk.
Absolutely. You absolutely do not want developers poking around in live customer data just to test a slow query plan.
Exactly. It violates every principle of data security. But with this new feature in Postgres 18, you can dump only the mathematical statistics from the production database using a specific command.
Okay.
You then inject those abstract statistics into a perfectly safe, completely empty testing environment.
So you're bringing over the metadata, but absolutely none of the actual sensitive information.
Correct. The query planner in the empty test environment will then behave exactly as it would in production because it is operating on the exact same statistical assumptions.
That's brilliant.
It really is. It allows engineers to accurately reproduce and debug complex query plans without ever exposing a single row of actual sensitive user data.
You get a perfect simulation of the problem
Yeah.
without assuming any of the risk.
Spot on.
If we pull all of these threads together, it really highlights a fascinating trend in how we build things now. We are moving towards a model where the most advanced engineering involves simulating reality or verifying danger while keeping the raw underlying data completely isolated.
It is the ultimate balancing act of modern technology. Whether it is a solo developer isolating their text editor from third-party code, or Meta isolating their servers from user links.
The core theme is creating rigid, secure boundaries.
Exactly. We want the benefits of infinite scale and artificial intelligence assistance, but we are increasingly desperate to maintain our individual privacy and technical autonomy.
Which brings us right back to that core tension we started with.
It really does.
If artificial intelligence can legally launder an entire open source library, and solo developers are retreating to their own completely self-written environments to maintain absolute control, what does the future of actual human collaboration look like?
It is a great question.
Are we all just going to become isolated managers of our own personal machine-generated ecosystems, never actually sharing our underlying code? Something to chew on next time you are approving a pull request. Catch you next time on Vocal Technologist.
Spoken Tech for your ears.